Morning, everyone. So today we have Yuval
So
Ishai with us. One of the leading people in theory of cryptography. He's an expert on proof systems and multi-party computation, and a lot of works on complexity theory and cryptography. And I'm looking forward to these.
Okay, thanks so much, Irit, and it's great to be here again. This is joint work with Nir, with Prahladh, with Ron, from whom I stole some of the slides, and with David Wu. And before beginning with the technical part, and it's great that Avi is here, for me it sort of brings back memories from my postdoc years. So I spent my postdoc in the area from late 1999 to late 2002. I was technically first joined postdoc at DIMAX and AT&T, and then I did a postdoc at Princeton University. But throughout this time, I was here a lot attending talks. And, just many of the people I met here inspired me. So there were these professors or senior people. Avi just came fresh from the Hebrew University to the Institute to start this computational complexity program. I didn't interact a lot with these senior people. Amit was not senior, he was a junior faculty at Princeton. He was my postdoc host. I did a bit of collaboration with Ronit and Joe Killian at NEC. NEC was the research lab close to Princeton. Then there were people of my academic age, postdocs. You can see Irit, Kobe, Dieter, Omer. I didn't interact a lot with Irit back then. Mainly, I knew her by Kobe Nissim telling me how great she is. Then they started this prequel to the differential privacy work, which received recognition later than it deserved. And then there were these students. So Avi had Eli Ben Sasson and Ronen Chartier as PhD students who visited him at the Institute. Sasha had this whiz kid from Russia, Misha Alekhnovich, who unfortunately tragically died in a rafting accident a few years later. And then there was this kid, Ryan. Again, the pictures are not as early as I wish they were. Who was a visitor working with Dieter as part of a research experience for undergraduates. Actually, I knew already back then that he's destined to greatness because Dieter said he was okay. So Dieter is someone who even back then had very, very high standards. He taught me about high standards. I have since forgot what he taught me, but Subhash, who was a student at Princeton, was very quiet. He was busy reading his advisor's PhD thesis. Yeah, so, one point of relevance to the talk is that I did this after preparing the talk, and all these yellow people are actually cited. So I guess that even today I'm greatly inspired by the work of all these people and what I learned from them. And another thing that happened around this time was this $1 million prize by the Clay Institute. Right, so there was a prize tag for the question we were all obsessed about, the P versus NP question. It was recognized by a $1 million prize. Now, even back then, today, it may sound like a kind of, it's not a joke, it's $1 million, but, obviously, not a lot for this kind of problem. Even back then, $1 million, we knew it was about the recognition, not about the money. But I think the irony, which is again related to my talk, is that this prize today is worth roughly 10 Bitcoins. And the whole Bitcoin ecosystem hinges on the intractability of NP problems. Right, so in a sense, there is a huge market cap, of course, beyond the other consequences on this problem. And in fact, the cryptographic part of my work, of this talk, is closely related to questions about scaling Bitcoin infrastructure efficiently. Okay, so in a way, this huge price tag that Bitcoin infrastructure puts on the P versus NP problem is also related to questions in cryptography that serve as partial motivation for this. And this guy, I don't know how many of Eli Ben-Sasson, he's a founder of a company that basically commercializes this kind of cryptographic proof systems that I'm talking about. Cool, so I'll give an intro. You know that not everybody here is a cryptographer or complexity theory, so I'll give a brief intro that motivates the main question of this work. Then I will introduce a new kind of proof system that we call a dot product proof. And I'll tell you about constructions and applications. Okay, and the applications are motivated by the intro part, and please feel free to stop me with questions at any point. Okay, so let's discuss connections between probabilistically checkable proofs. Okay, these are proofs with a probabilistic verifier, hardness of approximation, and cryptographic proof systems. Okay, so the center of it all is the PCP theorem, undoubtedly one of the greatest achievements of theoretical computer science. It gives us this amazing ability to take any proof for an NP statement or any classical mathematical proof and encode it in a way that supports super efficient probabilistic verification. So the verifier, this is like the ultimate dream of a lazy referee. Right, the verifier can toss coins and read the small number of bits in the proof, as few as 3 bits if you're happy with smallest error of 1/2, and decide whether to accept or reject. Okay, if the input is in the language, then there is a proof that makes the verifier always happy, and if the input is not in the language, then the verifier rejects except with small probability. And not long after, it was realized that this PCP theorem has consequences to the hardness of approximating natural optimization problems. Okay, perhaps the most immediate example is the MAX-3 problem. So in MAX-3, this is the optimization version of 3 we have a collection of clauses of weight 3. Okay, each clause is the OR of 3 variables or their negations. And the question is how many of these clauses, of these constraints, we can simultaneously satisfy. Okay, so we know by the Cook-Levin theorem that telling this exactly is NP hard, is as hard as NP. But can we do better by just approximating this number? Okay, can we get within 1% of the maximal number of constraints that can be satisfied? And the PCP theorem tells us that we cannot unless P is equal to NP. And to be more concrete, when I say hardness of approximation, by default, I refer to approximating within 1% or 0.99 approximation ratio. And when I say NP hard, I mean via a constructive reduction from your favorite NP hard problem. For instance, here we take the exact version of 3 so you have a 3CNF formula. You want to know if it's satisfiable or not. You have a polynomial time reduction to the gap version of the problem. So you map your formula, your 3CNF to another 3CNF, such that if the original one is satisfied, then the new one can be satisfied. So all clauses can be satisfied simultaneously. And if the original one cannot be satisfied, then not only can the new instance not be satisfied, but you can satisfy at most 99% of the clauses simultaneously. So there is a gap between all and at most 99%. And this is referred to as the gap 3 problem. And the PCP theorem can be easily used to give us such a reduction that establishes the hardness of approximating max 3 sat. Okay, the correspondence is kind of clear. Suppose that the PCP verifier makes 3 queries, so each possible choice of the randomness of the verifier, which determines some predicate of 3 bits of the proof, defines a clause where the input variables are the bits of the proof. Okay, so the prover, if there is a proof that is always accepted, this corresponds to an assignment that is satisfied by all clauses, and otherwise, you know, the fraction of clauses that can be satisfied corresponds to the maximal acceptance probability of the verifier maximized over all possible proofs. Okay, and this connection also holds in the converse direction when we interpret the hardness in this constructive way. Okay, so it is easy to go from the hardness of approximation to the PCP theorem. Why? Because the PCP verifier can just pick a random constraint and check whether it holds by reading 3 bits from the proof. Okay, the proof will be an assignment. Cool, so this is well known, but one very natural question is, what about exponential time hardness? So we just established that if P is not equal to NP, then it's hard to approximate in polynomial time. What about exponential time? Now you may say, why do I care about exponential time? Well, in a sense, exponential time is the new polynomial time. Okay, but certainly as a cryptographer, you know, going back to the Bitcoin example, if you had an algorithm for 3 CNF formulas that runs in time 2 to the n over 100, then you can use it to forge Bitcoins and become a billionaire. Okay, so, you know, exponential time, 2 to the little of n time, in some contexts is considered practically feasible. In certain cryptographic contexts, for instance. Okay, and that's a well-known open question. And what do I mean by ETH? ETH is exponential time hypothesis. I mean, we need to assume the analog of the P not equal to NP, and this is called exponential time hypothesis, which says that you cannot decide whether a 3 CNF is satisfiable with if there is a linear number of clauses in 2 to the little of n time. And the question is, can we use this worst case exact hardness assumption to derive hardness, exponential time hardness of approximation of max-3 sat? And this is open, and you know, you can similarly formulate a gap ETH problem which corresponds to the approximation version of this problem, and whether ETH implies gap ETH is a long-standing problem, and you know, it is implied by this will be implied by a dream version of the PCP theorem, where you can think about it in the PCP language as a PCP for the satisfiability of the 3 CNF, where the proof length scales linearly with the number of clauses. Okay, and this would imply when applying the left to right transformation, when writing it as a reduction to gap sat, this will imply a reduction where the number of clauses here will be, the number of variables here will be linear in the number of clauses here. Okay, and this would be enough to show that ETH implies exponential time hardness of approximating max-3 sat. Okay, so that's an open question. And
to connect it to the talk we saw a few weeks ago by Mitali Bafna, they constructed PCPs of size quasi, what do you call it? Quasi-linear?
Quasi-linear, yeah.
N times polylog.
Right. Yeah. So following the result by Reed and others on locally testable codes, there was a lot of optimism about pushing this to the PCP regime. There has been some progress, but we're not there yet. Reed, what's your current level of optimism? Or
maybe this year you got it.
Okay, after my talk, we'll figure it out. Yeah, but the point is that this is, the linear size PCP has other motivation. We'll talk about the motivation on the left soon. But there's also the converse direction here, and it establishes some kind of a barrier. Okay, if you want to show the exponential time approximation result hardness, at least via this CARP reduction, then you have to build linear size PCPs. So in a sense, this is a barrier. And also this left implication is some barrier because it is well known that 3 is the minimal lecture complexity of PCPs, of PCP theorem. You cannot teach it in less than 3 lectures. So this means that you cannot teach, this result, in less than 3 lectures. Okay, so it establishes this right to left implication, also gives us some kind of a barrier on the easiness of proving these results.
Is this a new result we're going to talk about now, or what is this extra error?
The left to
Yes.
right to left. No, it's just a different scaled version of this. It's not. When I say ETH hardness, I mean via a constructive reduction that respects the number of clauses. That basically, if you have 3 CNF with a linear number of clauses, this is what I mean by ETH hardness. It's just a scaled version of NP hardness, which respects the number of clauses up to a constant. Yeah.
When you say linear size PCP, you mean linear size PCP for 3 SAT?
Exactly. For 3 SAT or circuit SAT, it's the same, where the number, well, the proof length is linear in the number of clauses, not the number of variables. And because for these ETH problems, we consider 3 CNFs with a linear number of clauses, the distinction between, in the number of variables, distinction between variables and clauses doesn't matter.
But it's not that, I can maybe come up with a different PCP for 3 SAT that does something non-trivial, other than checking just a random clause. Did that also imply this arrow?
You mean right to left arrow?
Left to right.
Left to right.
PCP that does something more sophisticated.
If you have, I'll talk about other kinds of PCPs later, but again, I think that this two-way implication means that the 2 questions are effectively the same. So these hardness of approximation questions, at least in the strict formulation of the CARP reduction, are equivalent to the PCP, the classical PCP theorem.
So, every reduction can be encoded as some 3 SAT.
Sure, but I mean, that's right, but if the reduction has a polynomial blow-up, then this is.
No, but if it's linear size, then there'll be some linear size 3 SAT.
It's a linear size PCP for 3 SAT.
Yeah, this I
So
understand.
then it doesn't have a blow.
But the fact that the problem is 3 SAT doesn't mean that the proof actually needs to be an assignment, right? It can be something
No, the
else.
proof can be something else, but it gives you a different 3 SAT instance.
Yeah.
That's linear in size to the original 3 SAT.
I think they'll give something for 3 SAT.
Okay, so basically this is an open problem. The community is.
So I had a different question, but for IOPs, do we have linear size IOPs?
We do. Yeah, I'll talk about IOPs soon. And this has some specialized consequences to hardness of approximation, but nothing as natural as this. Okay, good. So whenever we get stuck, for many years, we change the question, right? We try to make it somewhat easier. So let's make the question easier by lifting the restriction on the width of the clauses. So now replace 3 SAT by SAT. Okay, so the left to right implications still hold, but now I'm not aware of any right to left implications. So if we want to prove exponential time hardness of approximating SAT up to a constant, does this require progress on PCPs? We don't know. Even in the original polytime regime, does this even imply the PCP theorem? Now, this is mathematically meaningless because, the theorem is true unconditionally, but can you get a 2-lecture proof, right, beat the 3-lecture lower bound of the PCP theorem by relying on this assumption, okay, or this fact? I don't know. I don't know how many of you thought about these questions, but it seems like when we lift the locality restriction, then the connection with the PCP becomes one-directional, okay, for all we know. Yeah, so that's a challenge. This is the first open question for my talk. Prove hardness of max SAT say, based on the ETH assumption, okay? And what I will do, I will further cheat by changing max-sat to max-lin. So now instead of or of clauses, you have linear equations over a finite field. You know, in my running examples, the field will always be F7, but you can think of any constant size field. And for this problem, again, we have the left to right implication, but not the right to left. But here I will give you an unconditional proof that yes, this is ETH hard via an explicit reduction. So you can take a 3-sat formula and reduce it to the gap version of this max-lin problem, where the number of variables will be linear in the and constraints will be linear in the number of clauses of your 3CNF. Okay, so we give the strongest version of ETH hardness you can imagine for this max-3-lin problem. And our proof will also be considerably easier, much, much easier than the proof of the PCP theorem. So again, you know, this does not give, unfortunately, this does not give a proof of the PCP theorem.
And is the gap like between something near 1 to something smaller?
So the gap, yeah, the gap. So here we cannot have perfect completeness in the language of PCPs. So the gap, yeah, the gap will be actually between something that's close to half to something smaller. Yeah, so here we know, assuming the 3-lecture law bounded, the answer is no. There is no. Yeah. Okay, good. So I finished talking for now about hardness approximation. Let's switch to talk about cryptographic proof systems. Again, so all these connections are just, you know, I would say, even if they're technically simple, they're very unexpected, okay? Especially the connection between the implication of PCPs to hardness of approximation. If you tell this to an outsider, to a mathematician never heard about it, this will look very impressive. The second connection may be more intuitive, namely now I'm talking about cryptographic proof systems. You somehow expect, right? When I formulated the PCP theorem, I formulated it as a kind of a proof system. Why do we even need cryptography? I'll explain this soon. But let me just say the bottom line, that the combination of the PCP theorem and certain kinds of cryptographic hash functions, just think of them as functions that behave like random functions in certain ways. Or you can model, if you are a complexity theorist, you can think of this as a random oracle, but it's not always needed. This gives us so-called succinct arguments. Arguments means that they're only computationally sound. They're sound against computationally bounded provers, and there are inherent limitations, you know, work by Avi and others that shows that you cannot get interactive proofs with soundness against unbounded prover that have short prover to verifier communication under some reasonable assumptions. Okay, so we need to settle for arguments, and succinct means that the communication complexity is small. Okay, and we do this by combining the PCP theorem and cryptography. But if you try to literally apply them to the PCP theorem, I think that Eli Ben-Sasson's initial efforts in the theorem was, let's optimize the PCP theorem, let's look at all the degrees of freedom, optimize it to death, and then implement it. And indeed, there was at least one paper written in this direction, but it still led to proof systems that are very far from practical. On the theory side, you can ask, can I make actual proof systems like succinct arguments where the prover runs in linear time? Because of the limitations of the current PCPs, we cannot get it via this route. Okay, so this has led the crypto community to look for alternatives, but before discussing the alternatives, let me zoom in a bit about how and why we apply crypto to move from PCPs to succinct arguments. So the first observation is that you cannot just take a PCP out of the box and use it in a direct interaction between the prover and the verifier, because the natural thing would be for the prover Okay, unless the prover can write the proof in the sky, which is not very practical, if there is only direct communication between the prover and the verifier, then if the verifier sends the PCP queries to the prover and then the prover responds, then the soundness guarantee is lost, right? Because soundness guarantee implicitly assumes independence between the proof and the queries. Okay, so we need to generate this independence, but we cannot afford to have the prover communicated the entire pie to the verifier because this is not succinct. Okay, so we need to somehow achieve independence, and this is done via a cryptographic hashing technique. And the idea, so H, you can think of it as a function that shrinks the input by a factor of 2. In practice, in Bitcoin, people use functions that map 512 bits to 256 bits. Okay, and these functions have the property that it is computationally hard to find collision. They shrink the input, so many collisions exist, but it's assumed to be computationally hard to find one. Okay, so the idea is that you take the PCP proof, you write it, the bits of the proof as the leaves of a tree, and then you use logarithmically many levels of cryptographic hashing to hash it down to a short commitment. Okay, this commitment, if the hash output is 256 bits, this commitment will be 256 bits. And this is committing in the sense that now if you ask the prover, hey, please open your proof, if you can open it in two different ways, then you can find a collision in the hash function. So assuming it's collision resistant, you cannot, it's binding. Once the prover gives me the commitment, it's bound to a specific proof. And another useful property, we cannot afford to ask the prover to reveal the entire proof. We need to locally, as a verifier, I need to locally query the proof. So the tree structures allows us to do this local opening. So if I want to query the fourth bit of the proof, then I ask the prover, hey, please reveal to me all the values on a path from the leaf to the root along with their siblings. And now I can check consistency of every two siblings with their child in the tree. And you can prove formally that if you can violate the binding property in this local opening, then you can find a collision in the hash tree. Okay, so this is a technique due to Kilian, the combination of PCPs and Merkle trees, and it was later made non-interactive in the random Oracle model by Mikali. Okay, so if you look about this approach is still used, and practical proof systems such as those employed by Eli company use this approach. Okay, the PCP plus Merkle tree, but with a different kind of PCPs I will talk about later. Anyway, this approach has two sources of redundancy. Why is this approach not practical? So as I mentioned, one bottleneck is the PCP encoding, which current versions of the PCP theorem they're not very nice in terms of computational complexity, even if you try to optimize them. But the second bottleneck, even if you had an ideal PCP, is that a PCP with good soundness inherently must make many queries. And each query requires opening this path on a tree. Okay, so when you compound these two sources of overhead, the soundness amplification, which requires us, we need very small soundness errors. So we need to make many queries in the PCP, not many, but I don't know, at least 40 queries in practice to the PCP. And then we need these values on the hash tree. So this makes the proofs not succinct. I would say 50 kilobytes to 100 kilobytes in practice. Even if you ignore the overhead, I mean, this has nothing to do with the overhead of the actual PCP. Okay, so trying to be kind of brief, so the crypto community came up with two kinds of relaxations. The first relaxation is to add interaction to the PCP model. This was actually initiated in a work by Kalai and Raz. It was titled Interactive PCP and was later generalized and called IOP, Interactive Oracle Proofs. And the idea is that the prover, as a standard PCP prover, writes a PCP proof for Oracle. Then there is a public random challenge, which the prover responds to with another PCP proof and so on. And in the end, the verifier can query all these PCP proofs, but the interaction component here is essential. And it turns out, again, the previous compiler I described works almost unchanged with this interactive version, but now we can have, this is much easier to construct than standard PCPs, both in terms of prover work, verifier work, simplicity. So this is a much lighter weight version of PCP theorem. Also with linear time prover in some models, there are still some major open questions there, but in some models we can get linear time proofs. So this is great, but again, it's not this succinctness bottleneck that I mentioned. This only sort of relieves the PCP cost bottleneck, but not the succinctness bottleneck that is part of the PCP model that you make queries to a proof, okay? And in order to make it more succinct, there was a second relaxation that we actually proposed in a paper from the CCC conference. So this was something, this is with Koshilevitz and Ostrovsky, where our main goal was to show that you don't need, again, it's mainly a simplicity goal, but we also observed an efficiency consequence. And the idea was, okay, classical PCPs are hard to construct. Let's make the set of queries richer. And specifically, let's allow linear queries to the proof. What do I mean by linear queries? Every query can take an inner product. Now the proof is a vector over a finite field. This is the proof, pi. And every query I make to the proof is an inner product of pi with some verifiers chosen vector of the same length. Okay, so now this is a 3-query linear PCP. Now you get these 3 field elements as answers. And given these answers and the input, the verifier decides whether to accept or reject. So this is the linear PCP model, same as standard PCP, except that we replace point queries that query single symbol of the proof by these richer inner product queries. Okay, it's a strict relaxation of the standard PCP model. And now the question is what this relaxation buys us. So it turns out that it buys us a lot. Okay, first of all, we can gain in simplicity. If you look at the ALMSS result, there is this so-called Hadamard PCP, which is also used as can it serve as a way to bootstrap Irit's recursive construction. If you strip down the linearity testing and self-correction part, so this is something that those of us who teach PCPs usually teach as a simple version of the PCP. Formulated as a classical PCP, it's of exponential size. But if we consider this linear PCP model, it becomes polynomial size, simple, and in fact much simpler than the ALMSS result because you don't need any linearity testing or self-correction because a malicious prover is effectively bound to a linear strategy, a linear function of the queries. Okay, so just to illustrate how simple this is, the PCP proof, if W is the extended witness, say that you want to prove the satisfiability of an arithmetic circuit, and W contains all the wire values of this circuit on a satisfying assignment, then the proof vector is just this extended witness and all degree 2 monomials, okay, the products of all pairs. Okay, so this is as simple as it is, and and another feature is that you can get soundness, which is 1 over field size with a constant number of queries. You can get something known as reusable soundness, which means that even if you try to reuse, this is useful for cryptographic applications. I'll skip this for lack of time, but basically it means that the same queries can be reused, such that even if prover tries to learn the queries by creating bogus proofs, they cannot violate soundness. They can be linear size, and in fact, you can compile a classical PCP into a single query linear PCP, and this we showed in 2013, but this compiler loses all 4 advantages listed above. It's not simple, soundness is worse, it's not reusable, and it's not linear size. Okay, so in principle, we can get 1 query linear PCP via the PCP theorem, and basically this talk is about getting something much simpler and better, which is a version of one query linear PCP. Okay, but
the answers of the prover to this linear queries, they are assumed correct. There is no, you verify them cryptographically or?
yes, so let me talk about how to, so there is it's harder to compile this kind, right? If we relax the PCP model, we expect to pay something. And what we pay is that we need a stronger cryptographic machinery. Okay, instead of using just a structureless hash function or a random oracle, now we use, if you want a clean abstraction, we can use certain kinds of homomorphic encryption, or you can just think of a random group oracle. So this is considered the simplest mathematical structure, right? This dates back to Diffie-Hellman. You assume that you have access to some a big abelian group, but you can't make sense of it. You cannot, say, compute a discrete log in the group, okay? So this is the type of cryptographic machinery that is used to compile such linear PCPs into proof systems. And again, this leads to practical proof systems that have advantages. They're much more succinct, so they can get the proof size to be, previously I said 50 to 100 kilobytes, now it's like 1,000 or 1,500 bits, okay? They're much more succinct. They have also some disadvantages, but you can also compose the two types of systems, and this is what is done today. This is the current trend today in practice, is to have an outer scheme based on IOPs, the previous version, composed with an inner scheme to give us the final ultimate level of succinctness. Okay, so this is, of course, they are slower because they use public key crypto, so this is, there is a trade-off, but basically, if you want to optimize succinctness in practical proof systems, you use linear PCPs and not standard classical PCPs or IOPs. Okay, this is the trend. Okay, so what I will talk about is an even stronger version of linear PCP called fully linear PCP. And here, it's kind of like, analogous to PCPP or PCPs of proximity, where the queries are made jointly to the input and to the proof. Okay, so now the verifier does not have direct access to the proof, but it can make joint linear queries, joint inner product queries to the input and the proof. And now we don't need access, as I said. Before we needed access to the input, now the verifier does not access the input. Again, it's restricted to these. Here, the verifier makes 3 joint inner product queries to the input and the proof. You can view this as a non-deterministic linear sketching. It's a different parameter regime. It's not, we were trying to mine the sketching literature, streaming sketching literature, did not find useful things. There are some non-trivial examples of fully linear PCPs implicit in the complexity literature. For instance, by Avi and Scott, they have a really surprising MA communication protocol for set disjointness or inner product language, which can be framed as a fully linear PCP with square root proof lengths and square root query complexity. So these things, some of these things are implicit in the literature. And in fact, you can take the standard LPCPs and make them fully linear at a small effort. This is true for most of the linear PCPs in the literature. Why is this interesting? From a crypto perspective, now you can apply the proof because the input is also queried linearly. Now you can distribute the input, you can secret share the input, and you can still apply it. So these proof systems have found applications in secure multi-party computation and even in distributed protocols where you want to achieve proofs. Okay, so in this work, we take the simplicity to an extreme, and we study the simplest object of a single query fully linear PCP, and we call it a dot product proof. It's actually Avi's fault that we use this name. We wanted to call it inner product proofs, but the acronym IPP was already taken by interactive proofs of proximity. Actually, it's not Avi, it's mainly Guy Rothblum's fault. We wanted to avoid the disputes in the Rothblum family about the IPP acronym, so now it's DPP. Okay, and why do we care about fully? The short answer is that our results are as interesting even if you drop the fully, even if you just care about one query linear PCP, everything I will say was not known before, but we get to the fully, so you can think of it as a bonus feature, and it also helps crypto applications, and it also simplifies composition. I will see this, yes.
So it's basically just a reduction to MAX-LIN, or is it different?
So it's a reduction to a generalized version of MAX-LIN where equality is replaced by membership in a set you can choose. So you can have a linear combination of variables belongs to some set.
It's the same set for every equation.
No, it can be different for every query because the verifier can decide which inner products to accept based on the queries. Yeah, but the connection is indeed there.
Huh?
Yes.
If I don't want a fully linear PCP, but just a linear PCP,
Yeah.
it's connected to the question.
Yeah.
Like the fact that max-3 sub, for example, is hard in the gap version. Does this give me a one query?
Exactly. So you can derive from the PCP theorem. For instance, you can take a PCP for 3 coloring or a gap version of 3 coloring and directly use it to get a one query linear PCP over Z3 where the proof will be just the coloring 0, 1, 2, and you just take the difference in a random edge in the graph, right? So this is another direct way of getting it from PCP machinery. But the PCP machinery will inherit all of the limitations of the PCPs that we want to avoid. Great question. Cool. So there are some things that are that follow from the literature. Not the fully part, but just the one query linear PCP. You can get it, even a better version of what Yotam suggested from Hastad's optimal hardness of MAX-LIN with some limitations, all these things. And we, as I mentioned, this compiler from classical PCP to one query linear PCP, which has also some features, but these are all either inherit the limitations of the PCP theorem that I discussed, or there was a previous construction that has quadratic size proofs and was limited to fields that grow with the circuit size for inherent reasons. So it's not just a technicality. So basically, we did not have anything what we need for proving the hardness of MAX-3 sub that I mentioned in the previous literature on linear proof systems. And this is our goal. So it's really motivated by the two application domains. On the right-hand side, from the right kind of linear size dot product proofs will imply ETH hardness for MAX-LIN that I promised at the beginning. And on the left, because we make only one query, we get better succinctness for cryptographic proof systems. So these are the two reasons why we're interested in this object. But of course, it's also a very natural type of proof system that is interesting on its own. Okay, so I have roughly 15 minutes or maybe a little more?
Okay, you can take a little bit more.
Good. So I'll tell you about the main ideas for the constructions. I think the applications I kind of explained at a high level before. So let me talk about definition constructions and open problems. So this is a definition to make everything formal. So we take a finite field F. We'll have two regimes. One is the small field regime where we view the field size as constant, and one where we view the field size as very big. There is an input of length m, a proof of length m. In the language, we consider finite languages because for this notion, similarly to PCPs of proximity, it's purely an information theoretic problem that makes sense even for finite languages, even if p is equal to np, right? Because of the linear access to the proof. The verifier cannot, even if the verifier is infinitely powerful, it cannot decide the language by making linear queries, okay? So the verifier just, so the language is some subset of length n vectors, and the verifier just picks from the clever distribution, picks some query vector f of length n plus m, because it applies jointly to the input and to the proof. and this accepting set, right? This is the set answering Zaev's question. This is the set you test membership to on the right. Okay, this is the accepted set, and completeness says that, you know, if X is in the language, then with high probability, at least C probability, there is a proof pi that makes the inner product in the accepted set A with probability at least C. This is the completeness parameter. And the soundness says that if the input is not in the language, then every even bad proof will be accepted with at most S probability. We assume perfect completeness by default. And in the case of perfect completeness, it's easy to see that the accepted set must have more than one element, because if it has exactly one element, then there is basically the language must be affine. Okay, with perfect completeness. Yeah, and then again, as I said, this is meaningful even for finite L, even if the prover and verifier are computationally unbounded, but you know, the constructions will be efficient. Okay, but we can talk about this object at the information theoretic level without worrying about computational issues. Cool, so we want to get a simple and direct PCP constructions. We want to beat parameters of known PCPs, linear proof lengths, and we want, in general, we want the soundness error to vanish with the field size. So our main results, we have two kinds of main results. The first is a small field construction. So here, think of the field size as constant. I use P, but this can be any finite field, not necessarily of prime order. And basically what we get is that for 3-SAT or an arithmetic circuit of size S, there is a DPP, you know, for the corresponding language, which where the proof size is linear in S up to polynomial in the field size. So this is where we assume the field size to be constant. The soundness error is 1 over square root of the field size. And the randomness complexity is logarithmic in the proof length. Okay, so this is one DPP theorem that we prove. And you can ask, where does the 1 over square root P come from? It seems wrong, but okay, let me first say that if the field has 2 elements, then you cannot get perfect completeness. Okay, but we get the same type of result with imperfect completeness. As I mentioned, when P is constant, the proof size is linear, which is a big open question for classical PCPs. And finally, one can show that this soundness error is optimal for the DPP model. Okay, so maybe it's not what you would expect. You would expect 1 over proof size, but for the DPP model, so in fact, this is a distinction between one perilinear PCP and DPP. For one perilinear PCP, you can use Hastad's optimal hardness for MAX-LIN to get something similar with some caveats that has 1 over P soundness error roughly. And here the best we can get is 1 over square root P. Yes.
If you want PCP with not constant queries, but polylog queries, can you get linear size proof?
For PCPs, no, I think only with n to the epsilon queries, and even there is some explicitness issue.
Does it also make sense to talk about the size of the answering set, like of this A?
It makes a lot of sense, thanks for the question. In fact, to get the hardness of approximation result, we need to have constant size A, because then we can make it 1 by just guessing. So this is, yeah, that's a good question. But to get the optimal soundness, the size of the answer set will be roughly square root of P.
Already here, the gap is between, it's not close to 1, or it's perfect completeness actually.
Perfect completeness, yes. Yes, so again, this you cannot get with the answer set of size 1.
But for the small field of size 2.
For small field of size 2, you cannot get perfect completeness.
The gap is close to 1. The
The
completeness
gap is yeah, it's between 1/2 and something smaller than 1/2.
Oh, so it's not close to one.
It's not close to one. Yeah, it's constant gap, but not close to one. Yeah. Yeah, so in the case of large fields, we get, basically we get something that is optimal up to the poly here. Okay, so pick whatever soundness you want, say 2 to the minus 40. Okay, so if the field size is polynomial, sorry, if the modulus, prime modulus is polynomial in your circuit size and 1 over epsilon, then you can get a proof for arithmetic circuit. So you actually gain by having a bigger field because you can natively handle arithmetic circuits over the same field. And now the proof length becomes strictly linear. In fact, 2 times the circuit size. Again, it's a circuit modulo P. The soundness error is epsilon, and we also get this reusable soundness feature that you don't get from classical PCPs. Okay, so this is, I will talk in the rest of the time that I have, I will focus on the small field result, which is kind of cleaner and has direct relevance to the MAX-LIN problem. Right, so the small field result gives us the MAX-LIN problem without PCP theorem, rare example of non-trivial ETH hardness of approximation. There is a recent result of Guruswamy et al. In the context of parameterized complexity that shows also ETH hardness of approximation. On the downside, the approximation ratio doesn't vanish with the field size. So in the context of NP hardness of approximation, this follows from Hastad's result, but using much beyond even the PCP theorem, so PCP machinery plus. So these results are quite technical. And in the case of large field DPPs, we actually get a nice crypto application to succinct arguments. Let me give you the bottom line so we can get proofs where the total communication is roughly 500 bits. This is for concrete realistic parameters. So this is like 3 times faster than previous practical systems, and 3 times shorter and 10 times faster on the verifier side than the standard, but with tons of caveats. So we need some pre-processing, which is input independent but not reusable. Okay, this is more of a theory thing that soundness is proved in the generic group model rather than standard assumptions. And finally, because of this very loose analysis in the big field regime, currently we can only get these practical parameters with poor level of soundness, but the first limitation is sort of inherent, but the second and the third are not. So I think that, basically I think that in some use cases, if you have, say, an energy constrained verifier, some device that works on the battery, these kind of proof systems can in fact be useful and therefore motivate optimizing the big field construction, which is the second result. Okay, so let me give you some idea of how we get this first theorem, the small field DPP. And the idea is similar to what you might expect if you work in this area of PCPs. We combine an outer component, and this will be a 4-query fully linear PCP, for the language, where the proof size is linear. So we're very happy with this, except that it has 4 queries instead of 1 query, okay? And now the natural approach is to combine it with an inner primitive, which is a DPP for a finite, a constant size language defined by the outer fully linear PCP. So effectively the language LIN, for which the inner DPP apply, is the language that verifies, that represents the verification algorithm of this outer FLPCP. And the fact about this, the nice fact about this DPP model is that composition is trivial, right? In PCP, you have to work hard, right? So Iritz work with Omer on assignment testers, which was a prequel to Iritz's simpler proof of the PCP theorem, was in part trying to make this composition more streamlined. In the DPP model, it's just trivial, because you query the input and the proof simultaneously. So just to get a sense, the composed proof consists of this outer proof of the fully linear PCP. And now for every possible randomness of the verifier in this system, you just include a proof for the length 4 language induced by the verifier here. Okay, so you just, the prover just enumerates, hey, I don't know what the verifier's randomness is, but for every randomness, I know what I should prove. And this is a finite, a constant size language, so let me include the proof for this language. Okay, and now what the verifier does is just, does the outer verification using these short proofs. Okay, so so with this composition, we get the first main theorem that I mentioned. And now let me tell you how it's actually quite simple. I will mainly describe, I will describe the inner component in detail and give you a rough idea of how the outer component is less novel. It's an abstraction and simplification of previous proof systems, linear proof systems. Let me describe the inner component, which is more sort of DPP-ish. Okay, the inner component really is where we explore the power of DPP, and this is also where the limitation on soundness will come from. Okay, so this composition will inherit, this will be the soundness bottleneck, the inner component, and we will inherit the efficiency of the outer scheme and the soundness of the inner scheme. Okay, so let's start with DPPs without a proof, right? This seems ridiculous, and indeed, standard communication complexity arguments tell us that non-trivial languages cannot have a DPP without a proof, right? This is just a linear sketch. If you take this inner product language, if you had such a DPP with good completeness soundness gap, then you will get the communication complexity protocol for inner product that beats the known lower bounds. Okay, so it's useless in general, but what about very simple languages? Okay, to give you one example, the language that contains only the old zero vector. Okay, so there is this old trick that was first used by Rothblum and Smolensky that says, hey, let's take just a random linear combination, and this gives us a test, a degree 1 test, whether the input is 0. Okay, so this is maybe the simplest example for DPP. Take an inner product with a random query vector and now check whether the result is 0 or not. And this is a DPP for the 0 language. Okay, can we use this to get a DPP for every language? In some sense, yes. Okay, so if we don't mind too much about the C versus S gap, we just want it to be positive, we can just guess. Right, the DPP verifier can just guess some input x0 in the language and then apply the previous DPP to check, whether x minus x0 is 0 or not. And if our input is in the language, this will create slight bias, tiny bias towards 0, which we will not have, right? So if the input is not in the language, then the inner product will be a random field element, otherwise it will be slightly biased towards 0. And in fact, you can use this as the inner DPP for the F2 construction. So if you only care about MAX-LIN over F2, this is all you need for the inner gadget, but it still doesn't tell us how to scale things for bigger fields, with good soundness. Okay, but if you want the inner gadget for F2, this is all you need. Okay, what happens when we want better soundness or perfect completeness, right? The previous thing did not give us perfect completeness. Okay, so let's look at this unit vector language, and the natural idea would be to just take a random sparse subset of the field and take, so unit vector language, the inputs in the language are just the n unit vectors of length n. Okay, so what would the natural DPP look like? You first pick the accepting set as a sparse subset of the field of size t. And now you pick your entries of Q at random from A. Okay, so let's say that A is 2, 3, then I take a random query vector over 2 and 3, 2, 2, 2, 3, 3, 2, 2, 3. Now I know that if the input is a unit vector, then I must get something from A, right? Either 2 or 3. And then actually, we had a strong feeling of reinventing the wheel here, but we're not able to find, to derive this super easily. The proof is elementary but annoying that this works, but it turns out, yeah, I'll be happy, if somebody has ideas of how to prove it in a clean way. But it turns out that if this sparse subset is chosen to have a square root of p elements, then the soundness error of this test is order of 1 over square root p. If you want to get a sense of how this works, if you pick an accepting set of size t, then it's not hard to prove that the soundness error is at most 2/3. Okay, because there are 4 options. Yes.
Is it unit, you mean just the standard basis, like?
Yeah, standard basis, yeah, 1 in a single coordinate and 0s elsewhere, yeah. So, so again, I will not go through this exercise, but it's a cute but slightly tedious argument even for t equals 2 to show that you have constant probability of catching. The probability of catching a prover here is 1/3 if t is 2. Okay, so at least 1/3, sorry. Good, so at least 1/4. Okay, and why is this the best possible, just to give you a sense of why we're stuck at 1 over square root t? Because we have 2 kinds of attacks, and it's optimal even for this specific language. When n is roughly square root of p, okay, if n is at least square root of p, then this is the best soundness you can get for this specific language. And the reason is that we have 2 kinds of simple attacks. One picks x pi and random, and then basically you make the inner product random, so the verifier must accept it with probability t over p. So t is the size of the accepted set. And the other kind of attack uses a valid proofs on the unit vectors, right? So every unit vector has a valid proof that will always convince the verifier. Again, this can be generalized to imperfect completeness. So if I take a combination of valid x pi pairs, specifically I take 2 times, so I pick at random 2 inputs in the language, EI and EJ, each has a corresponding proof, and I take 2 EI pi I minus EJ pi j, then you can show it's kind of like selecting 2 balls. You have balls of t different colors. What's the probability of picking 2 balls of the same color? So it's 1 over t. Okay, so if the inner product here happens to be the same as the inner product here, and there are only t different options, then we will get a valid value in A. Okay, so it's kind of a birthday type thing. And so these 2 attacks, one that succeeds with t over p, one with 1 over t, tell us that the best soundness is 1 over square root of p. Yeah, and one cute thing, maybe I'll take 5 more minutes. Okay. Yeah, so we have this thing with optimal soundness for a specific language, the unit vector soundness, that's a language that seems to exploit the very special language of this structure, the very structure of this language. Now, can we use this to get an optimal soundness DPP for every language? Right, and the answer is surprisingly simple, yes, if we're okay with long proofs, which are okay for the inner gadget. And what's the idea? First, suppose that our language contains exactly n words that form an invertible matrix. Okay, so it's an n by n invertible matrix. Now it's just a change of basis, right, to reduce it to the previous set. Okay, so now I just, the verifier needs to check that x times the inverse of this matrix belongs to the unit vector language. Okay, so, but again, this is a very special case. Okay, what happens in general? An almost general case is where the language spans f to the n. So this is a typical case where you have much more than n words in the language. They will typically span f to the n. In this case, you know, if the language spans f to the n, you can always complete this matrix into an invertible matrix, right? A simple linear algebra exercise, okay? Now, once I do this completion, this really defines a prover strategy. Okay, so the prover strategy, the honest prover strategy, if the input is in the language, the proof will be just the completion. Okay, and again, the claim that's easy to verify is that x is in the language if and only if there exists a completion of x into a y of the form x prime, you know, such that this is a row of the matrix, or y times a minus m inverse is in the UV language. So this gives us a very simple DPP with optimal soundness for every language, where the caveat is that the proof length scales with the number, roughly with the number of words in the language. So it doesn't work for general languages, but this is good enough for our inner gadget. Okay, so this gives us the inner DPP gadget. Yeah, so this covers this. I will not tell you a lot about the outer fully linear PCP. It's again, it kind of simplifies. If you want to learn about linear PCPs, I think this is not only more general, but also simpler than previous versions in the literature. But it basically makes a use of multiplication codes like Reed-Solomon codes or algebraic geometry codes to give a fully linear PCP with a constant number of queries. So unfortunately, I will not describe this part in detail. I'm happy to go over it offline. Should I?
Yeah, maybe you
okay.
can give us a couple
Good.
of words.
Good. So okay. So the canonical language that suffices for everything for a main result is this thing called rank 1 constraint satisfaction language. The language is specified by 3 matrices A, B, and C. The input is X. And the question, this corresponds to pointwise product. So basically you want to say, hey, if I take, so you can think of it as a language that allows you to check whether one linear combination of X times another linear combination of X is equal to a third linear combination of X. Okay, so you can see why you can take arithmetic circuit satisfiability and write it in this form, because X will just be the values, the outputs of multiplication gates. Now you need to check consistency of every output of multiplication gate with the 2 inputs of the multiplication gate, which come from another multiplication gate. Okay, so if X includes just the output values of multiplication gates in a satisfying assignment, then verification will pass, and vice versa. Okay, so this is just some convenient arithmetization of verifying an assignment to an arithmetic circuit. Okay, so this is enough, and let me define the primitive of multiplication code. So again, it's a nice abstraction of things you all know, right? So you all know Reed-Solomon codes, some of you know AG codes. This is sort of a simple abstraction that captures the essence that is useful for many, if not most, applications in computer science. And you can think of an encoding function from K to N and a companion encoding function E star, where E star is an encoding function of the square of the code E. What is the square of the code E? It's the code spanned by all pairwise, component-wise products of code words in E. So for every pair of code words in E, you take their component-wise product, and E star is an encoding function of the code spanned by these products. Okay, so basically we have that for every, think of this as E as a Reed-Solomon code defined by polynomials of degree 5, then E star will be Reed-Solomon codes defined by polynomials of degree at most 10. Okay, and if you take pointwise products of 2 code words in E, they will be evaluations of a polynomial of degree at most 10, which corresponds to a code word in E star. Okay, and AG codes give us something similar with constant size fields. And interestingly, we want to use codes with constant rate, and we want the distance of the code. So there is this distance parameter delta. This is a relative minimal distance. We want it to be very close to 1 because the soundness error will be 1 minus delta. Okay, so it turns out, and actually there must, I don't know if there is a relation, but it luckily turns out that for AG codes, this is from result from algebraic geometry, you can achieve constant rate with up to 1 minus 1 over square root field size minimal distance. So the square root comes up not only in the inner gadget, but also in the AG code. So we need some kind of conspiracy between it. I don't know if there is any relation between the two, but we rely on both this 1 over square root of the inner DPP and the 1 over square root that comes in the AG code's rate distance trade-off. Yeah, I suspect there must be some relation, but we don't know what it is. Cool, so how do we use such codes to build? The construction is really a two-line. What the prover does, right? So there is an input X, and remember that we can make linear, constant number of linear queries to the input to check whether, together with the proof, to check whether it is in this language. So what the prover does is the following. It takes AX, encodes it, takes a pointwise product with BX, and we know by definition of a multiplication code that this must be a code word of E star, so let M be the corresponding message. And we assume here that the codes are linear and systematic, okay, without loss of generality. Okay, so the fact that the codes are systematic also means that a prefix of M, so the dimension of this code is bigger, it's twice bigger, but we know that it's bigger, at least twice bigger, but we know that the dimension that the prefix of this message M must be the pointwise product of AX and BX. Okay, just because the codes are systematic. So the proof vector will just be M. So again, M is the condensed version of this pointwise product, right, of AX and BX. It's sort of a certificate. This is what you get when you multiply AX and BX, the encodings. Okay, this is the proof. Now, what does the verifier does? First, it needs to check that the prover indeed gave the right N. Okay, so M is indeed the message whose encoding is the pointwise product of the encoding of AX and the encoding of BX. Okay, so we're sort of checking a redundant version of the computation that we want to verify. Okay, and now we want to check consistency of this M with CX, which basically means that the prefix of M is equal to CX. Okay, because again, M is longer because this code has higher dimension, but it's systematic, so its prefix should be equal to AX pointwise product with BX. Okay, so this is the whole proof. Maybe it was fast to follow. And then this can be chosen, again, by relying on the high minimal distance of these codes, by just, this is the standard small bias test, right? You just check at a random coordinate that everything is satisfied. So we pick a random coordinate I and check that indeed this multiplication property locally holds. Okay, and then we check zero test by just, you know, the same random coordinate of a linear encoding, right? We need to check that M is equal to CX. This is the prefix of M, right? So we need to check that this is zero. We just check it using a random coordinate. So all this can be written as 4 linear queries, right? So all these things, you know, this is a coordinate of a linear code, a linear encoding. This is just one linear query, right? Another linear query, another linear query, another linear query. All are linear functions of the input and the proof. Okay, so this works. You can easily compress it to 3 queries, but we don't need it for the asymptotic result because it works for any constant size language. That's it. So let me conclude with, I already told you a lot about applications. We have some new cute crypto compiler from DPPs to cryptographic proof systems using generic groups. Let me conclude, just to mention that the large field construction that I did not talk about, it's very different. It uses some tricks of embedding into small integers. It's very much more technical than the first result that I talked about. And the result is very far from tight, most likely. So if somebody is looking for a nice technical problem with a crypto motivation, I think it's a nice one. There might be some textbook simple constructions that we entirely missed. Cool. So yeah, so DPP is a new kind of probabilistic proof system, very simple. We have efficient constructions that beat known PCP constructions, strong soundness, which is useful for crypto applications. We have two kinds of constructions. We have applications for hardness or approximation and for succinct arguments. Many open questions. Okay, if you're looking for nice open questions, I think there are many in this space. One, again, we showed that you cannot get, here Q is the field size. We cannot get 1 over field size soundness in the DPP model, but in the linear PCP model, 1 query linear PCP, we know how to get it with imperfect completeness from Hastad's hardness or approximation results. Can we get it with perfect completeness? Again, relating to Zeev's question, this would require us to have an accepted set of size at least 2. Right? So you can frame it as a hardness with a perfect completeness, of the gap version of a relaxed version of MAX-LIN, where instead of equals 5, you can have either 5 or 7. Okay? This is a hardness of approximation problem. I don't know the answer. I don't know how to get something like this without the PCP theorem. And also, it's conceivable that you can have a version of a DPP with linear access to input. We cannot get all the way to 1 over field size, but maybe if you allow quadratic access to input or some other type of limited access to input, maybe you can have a DPP-like notion, which has advantages for composition, and it's being purely information theoretic, right? It doesn't carry the baggage of complexity of P versus NP question to be meaningful. Yeah, this is the last question I mentioned. To get tighter result for large field DPP, we have this huge polynomial blow-up, right? So you expect the field size to be 1 over epsilon squared, and we have a big blow-up. And again, in the approximation, hardness of approximation results, either ETH hardness of more problems or more hardness of approximation without the PCP theorem. I mentioned the MAX-SAT problem, also MAX-LIN with optimal approximation ratio. Again, can we get this hardness result without the PCP theorem? Again, the fact that it's LIN and there is no locality makes it potentially easier than the PCP theorem, but we don't know how to prove it without the PCP theorem or with exponential time hardness. That's it. Yeah, so I'm done.
Okay, thank you very much. Any questions?
What if you use rings instead of fields? Oh.
Great question. I think that fields here are useful if your goal is to construct such systems and you don't care. I mean, if you want to work over rings, it's a different question. But if you're not restricted to work over rings, all the zero divisors only make things harder, right? So these proof systems crucially rely on a short zipper or things that don't work as well over rings. I mean, you could do it over rings if you really had to by using a suitable extension that has
It wouldn't help in anyone.
But
You don't think it would help?
you never know. In crypto, some branches of research do want. Sometimes you want, your machine's instructions. The multiplication is done modulo 2 to the n, integer multiplication. So you want your system, your proof system, to be over z2 to the n. So there are some lines of research in this direction, but it's not super mainstream. But yeah, it's an interesting question. What is the best soundness you can get for DPP over z2 to the k? I don't know the answer. My guess is that Yeah, I have no guess. Okay, cool. Yeah.
Okay, so thanks
Okay.
again.